Today, we're going to delve into the fascinating world of linear momentum. We'll cover 4 key concepts: the impulse momentum theorem, the principle of conservation of linear momentum, collisions, both elastic and inelastic, and finally, collisions in one dimension. Linear momentum of an object is defined as the product of its mass and its velocity. It is represented by the equation, P equals mv. Here, P stands for momentum, m for mass, and v for velocity. The SI units of momentum are kilogram meters per second, kg, meter per second. The direction of the momentum is the same as the direction of the velocity. Since velocity is a vector quantity, momentum is also a vector quantity. Let's relate this to some everyday scenarios. Imagine a fast-moving car and a slow-moving car of the same mass. The fast-moving car has more momentum than the slow-moving car. Similarly, a heavy truck has more momentum than a small car moving at the same speed. This is why a heavy, fast-moving truck can do more damage in a collision than a slow-moving motorcycle. The higher the momentum, the greater the potential impact. Let's talk about something cool in physics called the impulse momentum theorem. Imagine you're kicking a soccer ball. When you kick the ball, you apply a force with your foot. The harder and longer you kick it, the faster the ball moves. This is because you're giving the ball what we call impulse. Impulse is just a fancy word for the push you give to the ball over a certain amount of time. This impulse changes the ball's momentum, which is its speed and direction. Think of momentum as how hard and fast something is moving. Imagine these rocks are the same size as the soccer ball. If you push the small rock, it moves easily. But if you push the bigger rock, it's harder to move because it has more mass. So, to change the momentum of the bigger rock, you need a bigger push or a longer push. So, the impulse momentum theorem is just saying that the change in how fast and hard something is moving, its momentum, depends on how hard and how long you push it, the impulse. It's like saying if you want to make something move faster or in a different direction, you need to give it a good push. The impulse momentum theorem explains how forces change the motion of things. Next time you kick a ball or push a swing, remember you're using impulse to change its momentum. The impulse momentum theorem states that the change in momentum of an object is equal to the impulse applied to it. Mathematically, it's expressed as delta P equals F delta T, where delta P is the change in momentum, F is the average force applied, and delta T is the time duration over which the force is applied.
Imagine you have a billiard table with balls on it. When you strike the cue ball with the cue stick, you're applying a force to the cue ball. But once the cue ball is in motion and collides with other balls, the total momentum of the balls before and after the collision remains the same. This is because the system is closed and no external forces are acting on it, like wind or friction from outside. When the cue ball hits another ball, it transfers some of its momentum to the second ball. The cue ball slows down, and the second ball speeds up. But if we add up the momentum of both balls before and after the collision, the total amount is the same. Total momentum before equals total momentum after in this equation. P total before represents the total momentum of the system before the collision, and P total after represents the total momentum of the system after the collision. In a closed system with no external forces, these two are equal. Let's consider an example with numbers. Suppose the cue ball has a mass of 0.2 kilograms and is moving at 2 meters per second before it hits a stationary ball of the same mass. The cue ball transfers its momentum to the second ball. Let's see what happens. before the collision, the momentum of the cue ball is 0.2 kilograms times 2 meters per second equals 0.4 kilograms meter per second, and 0.2 kilograms times 2 meters per second equals 0.4 kilograms meter per second. The second ball is stationary, so its momentum is 0 kilograms meter per second. The total momentum before the collision is 0.4 kg meter per second. After the collision, let's say the cue ball slows down to half a meter per second, and the second ball moves at 1.5 meters per second. The new momentum of the cue ball is 0.2 kilograms times half a meter per second equals 0.1 kilograms meter per second, and the second ball's momentum is 0.2 kilograms times 1.5 meters per second equals 0.3 kilograms meter per second. The total momentum after the collision is still 0.4 kilograms meter per second. This is the principle of conservation of linear momentum in action. It's crucial for analyzing physical scenarios like collisions, whether it's billiard balls, car crashes, or even particles in physics experiments. Conservation of momentum. General law of physics according to which the quantity called momentum that characterizes motion never changes in an isolated collection of objects. That is, the total momentum of a system remains constant. Momentum is equal to the mass of an object multiplied by its velocity and is equivalent to the force required to bring the object to a stop in a unit length of time. For any array of several objects, the total momentum is the sum of the individual momenta. There is a peculiarity, however, in that momentum is a vector, involving both the direction and the magnitude of motion, so that the momenta of objects going in opposite directions can cancel to yield an overall sum of 0. In a collision of two particles, the sum of the two momenta before collision is equal to their sum after collision. What momentum one particle loses, the other gains.
Conservation of momentum is closely connected to Newton's law of motion. Newton's third law of motion states that for every action, there is an equal and opposite direction. Action and reaction force act on different objects. When two objects A and B are touching each other, if object A exerts a force F on object B, then object B will exert a force negative F on object A, for example F are equal, but in different direction. F of equals negative FBA. Momentum is a way to describe the motion of an object, which depends on its mass and how fast it's moving. Think of momentum as the oomph an object has when it's moving. When you and your friend push off each other, your combined momentum before and after the push remains the same. If neither of you were moving before the push, your total momentum was 0. After the push, you both move, but in opposite directions, so your momenta still add up to 0. This is the principle of conservation of momentum. Impulse is defined as the product of the force applied to an object and the time duration over which the force is applied. It is given by the equation, impulse equals F delta t. Impulse also equals the change in momentum, delta p, of the object. Impulse equals delta p equals m delta v. This tells us that we can achieve the same change in momentum with a large force acting over a short period of time, or a small force acting over a longer period of time. Lending your knees when landing. When you jump and land, your body needs to come to a stop. If you land stiff-legged, the time interval, delta t, during which you come to a stop is very short. This requires a large force to change your momentum to 0, which can be harmful to your joints. By bending your knees when you land, you increase the time interval over which you come to a stop. This longer time interval reduces the force needed to change your momentum, making the landing safer and reducing the risk of injury. Airbags in automobiles. Airbags in cars are designed to save lives by reducing the forces on passengers during a collision. In a crash, the goal is to bring passengers to a stop over a longer period of time. Without airbags, passengers come to a sudden stop upon hitting the dashboard or steering wheel, resulting in a very short time interval and thus a very large force, which can cause serious injuries. Airbags inflate rapidly during a collision, creating a cushion that extends the time interval over which the passengers are brought to rest. This longer time interval means that the force exerted on the passengers is reduced, lowering the risk of injury. In summary, both examples, the principle of impulse is at work. By increasing the time over which the change in momentum occurs, the force experienced is decreased. This is why bending your knees when landing and using airbags in cars are effective safety measures. They help manage and reduce the forces on the body, preventing injuries.